Yes, we see your screen too.
Okay, so hello, my name is Arseny Sorokin, as already was mentioned, and my talk would be concerning theoretical analysis of limiting factors for quantum noise squeezing of ultrashort pulses in optical fibers. So let's talk what all of this entails. So quantum noise is a fundamental uncertainty of light amplitude of phase, also called quadratures, caused by its quantum nature. So the reason the research for quantum noise is important so is that the fluctuations or quantum fluctuations can limit precision for many measurements and such as those used in interferometers or in some sensors. So it makes sense that we would want to decrease such fluctuations. One of the ways to decrease these fluctuations is to squeeze them with a kernel nonlinearity. So to explain what squeezing means in that regard. So imagine there is a light wave with some amplitude, and there are some fluctuations for two of its quadratures. However, if we apply the nonlinear process, such as a kernel nonlinearity in that case, the shape of those fluctuation distribution changes, and so if it was equal for both of axes before, it becomes an ellipse. So then, if we, for example, can rotate this ellipse, we could measure only the distribution alongside the shorter axis and get reduced fluctuations, get a reduced quantum noise. So if you reduce one noise for one of the axes, you always increase the noise for the other one because of the quantum uncertainty principle. However, there are several physical factors that can decrease the strength of squeezing attainable in the fiber, such as losses and Raman effects, and we will talk about how those effects make squeezing worse. Okay, so, and we do all of this with a numerical model. Of course, the quantum equations are very complex, but you can simplify them just stochastic nonlinear Schrödinger equations. We use a certain pulse with noise added as a starting point. It is important that for those solitons, the peak power is connected with the duration of those pulses. So the longer the pulse is, the lower the peak power. And there are several physical factors involving evolution of this pulse in this equation. There are some group velocity dispersion. There are factors connected with Raman and nonlinearity, such as Raman nonlinearity and kernel nonlinearity, the deterministic part of it, and the stochastic Raman noise, also caused by Raman nonlinearity. And there are parts connected with losses, and those parts also have stochastic parts, stochastic loss noise, and there are some deterministic losses. I know this a lot to take in, so I will talk about its impact later. The type of squeezing we are modeling here is called polarization squeezing. So what do we model? We model pairs of pulses with different polarizations as they travel along the fiber. And for those pairs of pulses, one is polarized with an x-axis polarization and the other with the y-axis polarization. Y. So, and we calculate Stokes parameters for those, and we model those pulses around 1000 times. So we those are the realizations of those stochastic equation because of the and stochastic parts. And then we plot the cloud of those realizations onto the plane S1, S2. So we can see the first picture on the slide is the cloud before the evolution, and the second is after propagating through the fiber. We can see that this cloud was squeezed, and the shorter axis is much shorter than the radius of the cloud. So the ratio between those two parameters is called the squeezing. It's measured in decibels. So it's important to mention because the axis decreases, so the squeezing in decibels is negative. So, and the lower this negative value, and the higher the absolute value of this negative number is, the better the squeezing. So there are several physical factors, as I already mentioned, that affect the squeezing. So let us talk about each of it in particular. So there is kernel linearity. Kernel linearity is the thing that makes squeezing in the fiber, and it scales with the peak power of the pulse. There is a certain analytical formula for Kerr squeezing in continuous wave regime. We are studying solitons here, so it's not exact, but this formula can provide insights into the what we should expect from those from the squeezing in this soliton regime. There are losses, and the losses effects are twofold. First of all, they decrease pulse power, and therefore they decrease the effect of the kernel linearity. However, it's not really the main issue with losses. The quantum thing here, as I can say, if it can be said that way, is that losses mix in the vacuum noise into our squeezed state that propagates through the fiber, and that decreases the squeezing tremendously. There is also an analytical formula for that, and it is also approximate because this formula assumes that all losses happen at the end of the evolution of this signal. However, this formula can be used too for approximations. And of course, the longer the pulse propagates through the fiber, the more losses influence its squeezing. There are also the Raman effects, which are a bit trickier. They change the pulse shape and also add Raman stochastic noise. And the important thing here is that, well, first of all, we need to use a special approximation in order to properly account for the lower frequency, because the usual approximation for the Raman function is the one which is denoted here with a blue dotted line. There's a real and imaginary part of the spectrum presented on the slide. But the more correct one, which is describes lower frequencies properly, is the one we use, and it's the one in the red line. And we also can see that with shorter pulses, there's much more overlap, and therefore shorter pulses get affected by the Raman effects a lot more. And so after we discussed all of this, we can finally proceed to the results of our modeling. So the first top three pictures show the results for solutons of different durations, with Raman effects, without Raman effects taken into account, and the bottom ones are the ones where we took the Raman effects into account. So we can see that for longer pulses, with longer duration, such as on the picture C, they need to propagate through the fiber more because their peak power is lower. As I already mentioned, it is tied to the length of the duration of the pulse, and therefore the squeezing gets hurt more by losses. Thus, we can assume that the longer duration pulses get limited by losses. We can also see on those pictures that if we use the analytical formula for losses, we get a upper bound. The higher estimate, the squeezing we find the formula is worse than the one with the distributed model. However, this is not that bad, and it can be used as estimate as it produces the similar evolution of the squeezing. But what if we add Raman effects into the account? So we could see the picture D and see that the squeezing for the shorter pulses is quite worse, and the evolution doesn't look like the one which is estimated for constant wave or continuous wave, as opposed to the one without Raman effects, where we can see, and for longer pulses, where we can see that this evolution actually models it approximates it quite well, and we can see that shorter pulses are limited by the Raman effects. So we can see that shorter pulses are limited by one physical factor, and the other pulses, the longer ones, are limited by the loss factor. So we can plot an optimal squeezing as a function of soluton duration and find out that there is an optimum between these two conflicting factors, well, they're not exactly conflicting. They both make squeezing worse, but one makes for shorter pulses and other for longer ones. And we can find out that the optimal squeezing can be achieved in the pulses of the medium duration, such as 300 to 400 femtoseconds. So that is basically my conclusion. The things I already mentioned. And so thank you for listening. You can ask questions now, I think.
Thank you for your presentation. Do you have any questions? So then I can ask some general questions. So you are modeling frequency comb generation in microresonators. Is it also can be used there?
So there are issues. I have modeled frequency comb generations in microresonators, and of course such a phenomena can appear in the microresonator. However, there is a certain issue, as far as I understand, concerning getting this squeezing out of microresonators. So in the models I used in microresonators, the coupling between the mode in the fiber and in the resonator was very low. Well, and if the coupling is very low, there are many losses, as this equation would understand, and therefore most of the squeezing just dies out. But this is why I don't think it can be used in microresonators unless you find out a way to get all of this power that circulates in microresonator unscathed.
Okay, but your task is to minimize quantum noise in these systems, or?
Yeah, the task is to minimize quantum noise in the system. Well, at least for one quadrature, but it's hard. The noise in the system can certainly be reduced, but I don't think that any of this reduction would leave the microresonator in some kind of sense, I'd say.
Okay.